Is the p-value dead? Yes, definitely it is. Or not? In recent years, a heated debate has erupted about whether p-values lead to misinterpretation and misuse. Some experts even call for them to be banned altogether. But is that justified? So let's have a look at the rise and fall of the p-value and answer the question if the p-value is still the way to go. But first of all, what is the p-value and when do we use it? Suppose you're a researcher and you want to know if a new innovative drug has an effect on body weight. To test this, you compare the new drug with a placebo. So the research question is there a difference in weight loss between the new drug and the placebo? In order to calculate a p-value, we must first formulate the null hypothesis and collect data. The null hypothesis is the new drug has no effect on weight loss. It is as effective as the placebo. And the opposite hypothesis, the alternative hypothesis, is the new drug has an effect on weight loss. Now we have formulated the hypotheses and we want to use a hypothesis test, in this case a t-test, to calculate a p-value. The p-value then helps us to decide whether to reject the null hypothesis or not. But to calculate a hypothesis test, we need data. To get the data, we conduct a study with 100 patients. We divide the patients into two groups, one receiving the new drug and the other one a placebo. And after 3 months, we measure the weight in both groups again and compare it with the weight before the treatment. Let's say these are our results. The average weight reduction with the new drug was 8 kg and the average weight reduction in the placebo group was 3 kg. So we have a difference between the groups of 5 kg. And now we can calculate the p-value. It is calculated with the help of the measured difference between the groups, the sample size, and the variation in the data. Strictly speaking, with the difference in the groups, the sample size, and the variance in the data, we first calculate a so-called test statistic t. With the help of the t-value and the t-distribution, we can then calculate a p-value. Let's say we get a p-value of 0.032. But what the hell does the p-value tell us? In order to understand the criticism of the p-value, we must first, of course, understand what the p-value is about. Let's have a look at this. The p-value tells us how likely it is to see a difference of 5 kg or more between the drug and the placebo groups if the new drug has actually no effect. What does that mean? We actually want to make a statement about the entire population and not just about the sample. In null hypothesis significance testing, we first assume that there is no difference between the drug and the placebo in the population, i.e., that the drug has no effect. So in a population, both means are the same. The p-value now tells us how likely it is that we will get a result like the one in our sample or one that differs even more if there is actually no difference in the population, i.e. the new drug does not actually work. Therefore, if the p-value is very low, for example 0.01, it means that such a difference or a more extreme one is very unlikely to happen by chance if the drug has no effect. In this case, you have evidence that the new drug has an effect on body weight, and it is common practice to reject the null hypothesis. On the other hand, if the p-value is high, for example 0.40, it means that the observed difference or a more extreme one could easily occur by chance. So you don't have enough evidence to say that the drug is significantly different from the placebo. And in this case, we fail to reject the null hypothesis. It is common practice to use a threshold of 0.05 for the p-value to decide whether or not to reject the null hypothesis. So now in simple words, a p-value smaller than 0.05 tells us it's really unlikely that we would see such a big difference in weight between the drug and the placebo, or an even bigger difference purely by chance. The new drug is probably really having an effect. A p-value greater than 0.05 tells us, this difference in weight, or a bigger one, could easily happen by chance. So the new drug might not be better than the placebo. Therefore, the p-value helps us to determine whether the new drug's effect on body weight is statistically significant or likely due to random variation. So, in summary, you want to draw a conclusion about a certain population, and to do this, you specify a null hypothesis, you collect sample data, and calculate a p-value based on the sample data. And the p-value is then used to reject or not reject the null hypothesis. Well, but these results are misleading, unreliable, inaccurate, and unscientific. At least that is what critics of the p-value say. Some journals, like the Journal of Basic and Applied Social Psychology, even bans the null hypothesis testing procedure. But why is the p-value criticized so often? Basically, there are 3 reasons why the widespread use of p-values is criticized. The p-value is misleading, the p-value is used mindlessly, and the p-value is unscientific. Let's start with the first one. The p-value is misleading. Why is that the case? There are many misinterpretations of the p-value. For example, one misinterpretation is a low p-value means the alternative hypothesis is probably true. In our example, this means that the p-value provides a type of probability indicating that the drug works, thereby making a claim about the alternative hypothesis. This is of course not true. A low p-value indicates that the observed result, or an even more extreme one, is unlikely under the null hypothesis, but it does not directly provide the probability of the alternative hypothesis being true. Another misinterpretation is that a significant p-value is a conclusive result, leading to the permanent rejection of the null hypothesis. But that is of course not correct. Why not? Well, every day millions of people around the world conduct research on a wide variety of topics, and they collect data. Due to the mass of research projects, every now and then a significant p-value will result purely by chance, although this effect does not actually occur in population. However, a sample was drawn that deviated far enough from the population by chance to produce a significant p-value. Of course, these results will now be published, which is completely correct. We only have a problem if the results are misinterpreted and regarded as conclusive. Only when similar results are consistently observed in replication studies can we begin to identify a reliable trend. So as more and more studies are published that consistently show a certain trend, you become more and more confident that the null hypothesis is probably not true. Therefore, just because one study shows a significant p-value, it doesn't prove that the null hypothesis is false. This study just serves as one piece of the puzzle in determining the direction of a certain trend. We can therefore conclude that this point of criticism is partly justified. If you don't know exactly what the p-value means, then a p-value can be misleading. However, depending on how you look at it, this is not the fault of the p-value. The second reason for criticizing the p-value is that it is used mindlessly. Some critics argue that the low quality of research is because only p-values matter and researchers only search for significant results. Why is there such a criticism? Just because something is significant doesn't mean that the effect is relevant. A low p-value does not necessarily mean that a finding is of major scientific interest. Let's say in our example we get a p-value of less than 0.05, i.e. a significant result, and the measured weight difference between the drug and the placebo is 0.4 kilogram over the 3 months. Now you can say, okay, we have a significant weight difference of 0.4 kilogram, but perhaps this difference is so small that it is not relevant in practice. If only the p-value is published in a study, this could be misleading. Furthermore, the use of the p-value encourages dichotomous thinking. The null hypothesis is either rejected or not. Often research reports are simply skimmed quickly to find the p-value, and very quick judgments are made. Therefore, the p-value is often used uncritically as the ultimate measure without thoroughly examining the results. I would say this point is therefore partially justified. But again, it is not the fault of the p-value itself. And the third point of criticism is that the p-value is unscientific. Some critics mention a pressure to achieve significant results in scientific research. Unfortunately, I'm also aware of this practice from many years of supervising theses and my work in academia. Since the p-value is so much in focus and there is a lot of pressure to find a significant p-value, some people simply search their data sets to find a significant p-value, and if they find one, the appropriate null hypothesis is formulated afterwards. This is of course not correct and not scientific work. So should we finally ban p-values and no longer use them in our research? Let's discuss this with an example which you can see in the graphs below. In this chart, we can see study A and study B. In addition, we see a group of patients who have received a new drug and a group of patients who have received a placebo. The difference between the two groups is the effect size, which is what, for example, the editors of the Journal of Basic and Applied Social Psychology want authors to focus on. In study A, we can see a big difference between the two groups, and in study B, the difference is quite small. So now the big question is, which study found a true effect of the treatment and which didn't? The truth is that the results from both of these studies could represent either a true treatment effect or a random fluctuation due to sampling error. So how can we know? How can we get the right answer? This is where 3 factors come into play. Number 1, effect size. Number 2, the sample size. And number 3, the variability in data. What are effect size, sample size, and variability? The first important factor is the effect size. The larger the effect size, the less likely it is to be a random result. In the graph, we can clearly see that study A has a larger effect size. The large effect size seems significant, but it is not enough information to draw a conclusion. The second factor we need to look at is the sample size. The larger the sample, the more credible the results. Therefore, with a large sample size, you will be able to detect smaller effects. If the sample size for study B is large enough, it is very possible that the smaller treatment effect in study B is real. Finally, the variability in the data is important. The greater the variability, the more likely it is that we will see large differences between the experimental groups due to random sampling error. If the variability in study A is large enough, its larger difference may be due to random error rather than a real treatment effect. So, if the effect size of either study is meaningful depends on the other factors. The larger effect size in study A could be random error, while the smaller effect size in study B could be a true treatment effect. So wouldn't it be nice to have one main number that brings all this together, the effect size, the sample size, and the variation in the data? Hold on a second. That's exactly what the p-value does. The p-value combines the effect size, the sample size, and the variance of the data into one key figure. Therefore, we can conclude that the p-value is an objective standard for us, which helps us to assess the results from a study. However, we can also state that the p-value is not a magic number. Just as the effect size, the sample size, the variance, and any outliers must be critically questioned, the p-value, which is simply speaking just a combination of these three parameters, must also be critically questioned. And to interpret the results of a study, you should of course not just look at the p-value. Maybe, although a significant p-value was found, the effect itself is only small and of no practical relevance. So, what is the conclusion? We conclude that using p-values and the null hypothesis testing is still a valid way to go. Mindless statistics are not limited to p-values. So no matter which statistical indicator you use, always try to make sure you know what you're doing and be transparent about your research. And further, it is also not a good idea only to use the p-value. It is good practice to show all important indicators such as effect size, sample size, and descriptive statistics. In this way, the results can be verified by other researchers, and it gradually becomes clear whether a certain trend is confirmed or not. So, of course, we see criticisms of the p-value and null hypothesis testing procedure, but blaming the p-value alone is perhaps a bit short-sighted. More importantly, we believe the journals need to pay more attention to the quality in the review process. In the same way, statistical software can also make a contribution and, for example, help you interpret the calculated results so that no serious misinterpretations occur. For example, using DataTab, we can copy our data that we want to analyze into this table. Then we click on Salary and Gender, and DataTab will automatically calculate a t-test for independent samples. Here you can see the results. The hypotheses appear first. You find the null and the alternative hypothesis here. Now you click on Summary in Words, and all results will be summarized in words for you. In addition, there is an AI interpretation for almost all tables. So if you don't know exactly what the results in a table mean, you can simply click on it. But in general, what can we do to improve the quality of our research? How can we make our results more reliable and meaningful? Is there a way to improve the quality of research? Let's discuss this in my next video. Depending on when you watch this video, the second part may already be online. Otherwise, subscribe to our channel to find out when it's available. Thanks for watching, and I hope you enjoyed the video.